My name is Ryan Wallner, and I'll be your moderator for today's DoK Community Town Hall meeting. And we're going to have Thang jump on a little bit later after the community update to present Kafka on Kubernetes Reloaded, fault tolerance at Grab. Before we get into that, we have a few community updates to walk through real quick. As always, DoK community sponsors, we'd like to thank you, our gold sponsors, Google Cloud and Percona. You can visit the link below, DoK community/sponsors, to find out more about other sponsors such as our silver sponsors and our community collaborators as well. So thank you to all those sponsors, of course, for the DoK community. A few spotlights in the DoK community. The first one from Alvaro Hernandez. He was featured on the Kubernetes podcast talking about Postgres on Kubernetes. Go ahead and use that QR code to go check out that podcast. And Gabrielle Bartolini has another blog post on Cloud Native PG Recipe 8, participating in the PostgreSQL 17 testing program in Kubernetes. Also, go check out that QR code to find Gabrielle's blog post. We want to highlight the Women in Cloud Native community, really celebrating learning and supporting one another in the cloud native space, and really kind of fostering the diversity in the cloud native space. So there will be an event later in July, I believe. We'll cover that in a second. That will have more information on this specific community as well. But go check this Women in Cloud Native community out for sure. A quick update on our DoK Ambassador program. All the applications are in, and current new ambassadors will be announced later in July or the first week of July. So keep a lookout for that if you did submit a application to become a DoK ambassador. Those are being decided now, so very exciting stuff there. Of course, DoK Day at KubeCon North America in Salt Lake City will be on November 12th. So CFPs are still open until July 14th. So if you haven't submitted your CFP for DoK Day, we highly encourage you to go ahead and do that. You still some time, a little under a month left. So definitely want to see some more CFPs there. So please go ahead and submit those so you can participate in the DoK Day in Salt Lake City. A few upcoming events. One I mentioned earlier, which is the next town hall in July. This will be the Women in Cloud Native presentation by Nancy, one of the founders of this community. That'll be on Thursday, July 18th. Definitely want to go check that out. And July 23rd, there will be another DoK talk, Doc Talk, on the anatomy of DBaaS, bringing self-service and databases to Kubernetes with open source, and that'll be with Peter from Percona. So definitely stay tuned for the July events in the DoK community. That will be registered on meetup.com. So use that QR code, or you can go search for the DoK community on meetup.com as well. Lastly, we do want to encourage, if you aren't part of the DoK community yet, go ahead and join us. We always like to have new members. Or if you know anybody in the cloud native space that really wants to be a part of this, or you think they would like it, go ahead and send them the DoK community. Always looking for more members in our community. And if you want to become a sponsor at your company, go ahead and check out the sponsorship page as well. Before we dive into the talk today from Thang, I want to just say there'll be a quick quiz at the end where you can win one of these t-shirts, the Run DoK t-shirts. There'll be a set of very quick questions at the end. The fastest to answer them correctly will win this t-shirt. So stick around to the end to participate and win one of these t-shirts. All right, that is all for the community update. Thank you for joining today, and I'm going to hand it over to Thang. Go ahead, Thang.
Okay, so hi everybody. Thank you for joining me today on my talk about Kafka on Kubernetes. So I'm Thang, a senior DevOps engineer at Grab. So for today, I'll be going to a few items. So first of all is background and challenges. So I'll take a quick look at our initial setup of Kafka on Kubernetes and the challenges we have faced. Then for solutions, we have those will be the solution we have implemented to overcome the challenges. Moving on to operational improvements we have achieved with the solutions. Lastly, the future enhancement, how are we going to keep moving forward? So starting off with background and challenges. Grab, we started off a company of ride hailing over here in Southeast Asia. And ever since we started, we have grown to different business lines such as ride hailing, food deliveries, and express delivery. So with that, we also have a few different Kafka usage at Grab that we are doing. So first of all is to facilitate microservices communications. And we also have real-time application processing. So those the application that do handling ride bookings or handling payment transactions, for example. Lastly, we also use Kafka as a big data entry point. So it's to facilitate sync data such as change data capture, or in short for CDC, to our data lake. One of the use cases may be for analysts to query business metrics. So our Kafka setup currently run on Amazon Kubernetes service, which is a managed service for Kubernetes offered by AWS. Underlyingly, there will be EC2 instances that are running as our worker nodes within the cluster, and all of them are running in Amazon Virtual Private Cloud. So within our Kafka cluster, we also have Streamy Kafka operator, which I'll be going through in more details later on. Then there's other components such as crew control, a tool used with Kafka to automate the management and balancing of our Kafka clusters. And lastly, Zookeeper, a coordination service for Kafka to manage our local configurations such as leader election and tracking the status of nodes in the cluster. So going in more detail with Streamy, how we are leveraging Streamy as a Kafka operator over here at Grab. So Streamy offers us a few functionalities. So it helps to automate Kafka deployment, scaling, and configuration of our Kafka cluster in Kubernetes, and thus reduce manual intervention. Secondly, it also helps us to ensure high availability and resilience in our Kafka cluster with features like automated recovery, seamless upgrades, as well as rolling updates whenever we want to roll any configuration changes. And lastly, using Kubernetes operator framework, Streamy integrates seamlessly with Kubernetes, which is something we are looking for exactly. So to go to usual Kafka setup on Kubernetes in Grab. So usually we'll be going to a sample design of a 3-node Kafka cluster. So for our initial design, each of the node will belong to an auto-scaling group on AWS, one per availability zone. So in this initial design, our auto-scaling groups are not for auto-scaling because we want to keep the size of the cluster under control. So we only use AHEs with a fixed size to facilitate manual scaling operation and to automatically replace the terminated worker nodes. So moving on, since our Kafka is set up with rack awareness, Streamy as our operator will also add Kubernetes node affinity by default. So that also allows our Kafka broker pod to be evenly distributed across the nodes. So in our setup, it will be distributed across availability zones as well. So within each of the EC2 instances, there are also NVMe instance store volume, and they are used to create a Kubernetes persistent volume and then attach to a Kafka pods via the persistent volume claim. So for each of the Kafka cluster, there will be 4 different Kubernetes services. So one for the initial connection, which we are usually referring to as a bootstrap service that will redirect incoming traffic to any Kafka pods, plus one for each of the Kafka pod. And these are for the clients to target each Kafka broker individually, which is a requirement to for our clients to either produce or consume from a partition that resides on any particular Kafka broker. So following that, there will be 4 different listeners on the AWS Network Load Balancer, listening on 4 different TCP ports. So this will enable the Kafka client to target either the Bootstrap service or any particular Kafka broker that they need to reach. So with this entire setup, that also enable our Kafka cluster to be accessible beyond its own VPC via a VPC endpoint service. So now comes the challenge when one of our worker node gets terminated. So in this particular example, so looking at worker node C on the right side here. So when worker node C is being terminated, so by nature, ASG will spin up a new worker node. We call it worker node D. So worker node D will come up with an empty NVMe instance store volume. And then it will also automatically join the Kubernetes cluster. So the old Kafka broker tree pod that was running on the old worker node C is now scheduled to start on the new worker node D, which is a nature and a part of Kubernetes that we benefit from. However, during this process, Kafka clients producing or consuming from Kafka broker T partition leaders face connection error due to the broker's abrupt termination. And following that, the NLB target groups for the Bootstrap connection and Kafka broker tree is still pointing to worker node C at this point of time. And that will break any network communication to and fro these 2 services. So with that, currently what we are doing is our engineers need to do a manual reconfiguration for target groups. And following that, the persistent volume claim of Kafka broker tree cannot automatically switch to the new volume on the new worker node D because of Kubernetes static provisioning. So even though the PBC is still in a bound state at this point of time, the actual storage is gone because the old worker node is terminated. So with that, Kafka broker tree pod is unable to start. So at this stage, our Kafka cluster is running with only 2 out of 3 brokers until our engineer manually intervene and reconfigure the NLB target group, as well as deleting the zombie PVC, which will then trigger Streamy to recreate using the new instance storage. So what have we done? What are the solutions we have implemented to overcome these challenges? So let's recap. There are 3 main issues that we are facing. So first of all is interrupted client connections. So Kafka clients experience connection errors because the broker is abruptly terminated. Secondly, we also had network communication breakdown because NLB target group still point to the terminated node. And lastly is we need to deal with manual storage provisioning because the PVC does not automatically switch to the new volume. So that prevents the Kafka broker from starting until manual intervention resolves the issue. So with challenge number 1, our first solution is to handle Kafka shutdown in a graceful manner. So we achieved that with the help of a component called node termination handler. So this component provided by AWS for Kubernetes environment is able to cordon and drain a worker node that is going to be terminated. So this draining process in turn will trigger a graceful shutdown of the Kafka process within the pod itself. So it does this by sending a graceful term signal to all of the pods draining worker node, but in the focus right here is the Kafka broker pod. So instead of they send the graceful secure signal instead of the disruptive secure used in a normal termination. So that will allow us to gracefully shut down a Kafka broker in this scenario. So to go through a little bit about node termination handler, usually we can configure to operate in 2 modes, IMDS as well as queue processor. So the difference between IMDS and queue processor is that the latter capture a broader range of termination event taken from another service called AWS SQS, which is a managed queue provided by AWS. So that also offer enhanced fault tolerance and a more comprehensive coverage of events. So that is also the reason why we chose to go with that particular mode as well, because it will help us provide a greater fault tolerance for our cluster. So there are three key termination events that is captured by node termination handler that interest us. So those are scale-in operation, which is something that is typically triggered manually during our maintenance period. Secondly is a manual termination of an EC2 instance. And lastly is what we call AWS maintenance events. So these are the events, for example, in EC2 instances scheduled for retirement because AWS need to retire the underlying hardware. So node termination is also known to capture an event for spot instance reclaims, which is probably a more common use case for it that the open source community know of. However, it's not of interest for us, and we don't mention it here because we don't exactly use spot instances for Kafka. Now, let's try to understand how does node termination handler work. So, all the events, because we are using the queue processor mode, the events are all issued to AWS SQS queue. So the node termination handler itself, which is pod that we install and is running within the Kubernetes cluster that is operating our Kafka cluster, will constantly pull that SQS queue for new events. So upon receiving any event, so the node termination handler will send the Kubernetes API the instruction to then cordon and drain the worker node. So on draining, Kubernetes will then send a SIG-term signal to the Kafka pod residing on the worker node. And in turn, upon receiving the SIG-term signal, the Kafka pod will gracefully migrate the partition leadership of its partition to other brokers of the cluster before shutting down. So this is a very transparent manner for clients. The clients will then have proper timing to move over to the other brokers before the Kafka broker tree, in this example, shut down. So let's dive deeper into the events that node termination handle. So first of all is AHE scaling. So as soon as the scaling operation is triggered, there will be an lifecycle hook called auto-scaling lifecycle hook. Is then invoked to pause the termination of the instance. So simultaneously, the lifecycle hook event is also passed to the according SQL queue that node termination handler is pulling from. And with that, it also continue to do what it does upon receiving the event. And then once the impacted worker node has been drained, the lifecycle hook is then released and instant termination is then resumed. So there is the key configuration that we need to take note of for this to ensure a smooth and orderly termination process of Kafka broker during Kubernetes drain. So for that, we need to look at a parameter called termination grace period in seconds parameter. So this is the container lifecycle hook configuration that allow Kafka broker pods enough time to shut down gracefully. So by default, is set to 90 seconds, but then you can also adjust it based on the number of partition per broker. So based on our cluster traffic that we are benchmarked, we adjust this configuration based on 10 partition per second. But your mileage may vary and you might need to benchmark for your own cluster traffic to find a suitable configuration value. Diving deeper into the other two events, which is EC2 termination and AWS maintenance event. For these two flows, the events come directly from EC2 and AWS health. which is then published to SQS queue via AWS event bridge. And after which, node termination will handle the event accordingly. Very straightforward and very similar to AHE flow. However, there's an issue with each of these events handling. So looking back at EC2 event flows, there's an issue. The instance is immediately terminated at the same time the event is sent out. Most likely before the leadership of all its Kafka partition broker has had the time to get migrated to other broker. So that defeats the whole purpose of us having node termination handler, because it's not able to handle this type of cases. So with that, to work around this and let a manual termination on EC2 instance also benefit from the AHE lifecycle hook that I mentioned about earlier on, the instance must be terminated using the AWS CLI command, which is called terminate instance in an AHE. So how does this command actually work? So as soon as the engineer triggers the EC2 termination via the CLI command, as compared to via the AWS console, AHE will handle it. And as the result, we also benefit from the AHE lifecycle hook flow that I went through earlier on. So making this entire process once again graceful. So coming back to AWS maintenance events, let's zoom into when node termination handler receives the event. It will then cordon and drain the worker node scheduled for retirement. So at this stage, it will cause the Kafka pod state to become pending. At this point, the pod has nowhere to go because it is now stuck. So now there is a need for spinning up a new worker node for it to be able to eventually start somewhere. So to make this happen seamlessly, we doubled the maximum size of each of our AHEs, as well as installing the Kubernetes cluster autoscaler. So going back to the scenario, now when a Kafka pod is stuck in pending after cordon and drain, CA will then proceed to scale out the AHE. Then a new worker node will be provisioned and join the cluster. Then subsequently, the Kafka pod will also be scheduled onto the new worker node. Then lastly, after a period of time, cluster autoscaler will then detect the old worker node being underutilized and will proceed to terminate it. Okay, so there are a few considerations that we need to take note of when taking care of this flow. So when such event happen, the impacted Kafka pod for our case will be stuck in pending state for about 4 minutes. So during these 4 minutes, our cluster autoscaler will scale up the AHE. Then EC2 instance, it will spin up a new EC2 instance. It will need to boot up, join the cluster, be marked as ready before the pod eventually gets scheduled. So that's 4 minutes in total. And then there's also be cases when AWS is trying to retire multiple different underlying hardware, and that will affect multiple different instances within our cluster. So with that, to gradually rotate our instances one at a time, we implemented a pod disruption budget to set a maximum downtime of 1 pod at any point of time. So with that, Kubernetes scheduler will honor the configuration, and during the drain process, it will only drain 1 node at a time. So moving on to the next solution is I'll go through on how we manage to dynamically configure our NLB target groups. So to automatically map the NLB target group with newly spun up EC2 instances as compared to manual intervention like what our engineers have been doing previously, we leverage a component called AWS Load Balancer Controller. In short form, it will be LBC. So here is how it works. So firstly, the LBC will retrieve the desired state from a Kubernetes custom resource of type target group binding, with each resource linking to a target group linking a target group to a particular Kubernetes service. So for example, there will be a target group binding CR binding broker one service to a broker one to the according target group within the NLB itself. It will then monitor changes in the Kubernetes service referenced in the within the CR that we define. Specifically, you'll be looking at the private IP addresses in the respective endpoint resource that is bound to the particular service that it is monitoring. So when such a change is detected, which is when we spin up new EC2 instances, the LBC will dynamically update the corresponding NLB target group with the new IP addresses. So this will help to ensure that our NLB target group are always up to date with the current state of our Kubernetes service. Also, as well as automating the entire process, we no longer need any manual intervention. So this entire flow looks good, but it actually does not work for our implementation. So there are actually two issues. So the first issue that we have faced is when our rolling deployment is happening way too fast. To understand this issue clearer, so let's briefly go through how a rolling deployment would work whenever we make any changes to our Kafka cluster. So when any change is made, Streamy will start to rotate our Kafka broker in a rolling deployment status. So it will rotate the broker. Then secondly, Streamy will wait for the broker to be in ready status. So this means that Kafka process is fully ready and the new broker has successfully joined the cluster. Then it will continue to move on to rotate subsequent brokers. So bringing LBC coming back into the picture. So when the broker pod is rotated, subsequently, it will also go into ready state. And that also means that the equivalent Kubernetes endpoint resource also get updated. And that is a signal for LBC to update the target group. Afterwards, NLB will start a process to evaluate health check for the new configuration of the target group. So at this point of time, NLB will not let any traffic pass through. So this is the key point that we need to take note of. And that will only change when the health check passes. Passed. So the issue we face is that while the target group update and NLB health check evaluation are still in progress, Streamy has already moved on to rotate the other brokers. Then moving on to the second problem is that the entire health check flow of NLB is way too slow, and that causes problem for us. So when a new Kafka broker pod is spun up and reaches the ready state, it also means that the broker has successfully joined the cluster and is now ready to receive traffic from clients. So naturally, client will then attempt to connect to the new Kafka broker. But the problem is that they will encounter connection timeout issues because the NLB health check evaluation is still ongoing. So like I mentioned, NLB will only allow traffic to pass through as soon as the health check evaluation passed. So this issue will also subsequently affect other brokers when Streamy rotate them. So to mitigate the first issue of loading deployments happening too fast, we configured AWS Load Balancer controller with a pod readiness gate. So this feature ensures that Streamy's rolling deployment will wait for the NLB health check to pass before the pod is marked as ready and proceeding to the next pod. And for the second issue, we have reduced the health check interval seconds and healthy threshold count parameters of each target group. So these are a configuration of an NLB target group to their minimum value, meaning that we will reduce the entire flow to only 10 seconds as to the default value is up to 30 seconds. So to walk through how a flow of the pod readiness gate work. So when a old pod is terminated, a new pod will then will then start up and be scheduled onto maybe another node. So by default, by nature, LB load balancer controller will monitor service, see is get updated, will then it will go and proceed to update the target group. So the additional logic that pod readiness gate is that now load balancer controller will also wait for the NLB health check to pass before allowing the pod to be marked as ready. So this entire flow will slow down the rolling deployment by Streamy, and it will reduce the chance that our client will face connection timeout issues. Okay, coming up to the last solution, we have also changed the way we do data persistence of Kafka utilizing AWS EBS. So going to AWS EBS, so even though it's less performant as compared to the existing setup of NVMe storage, but there are a few key things that eventually we decided to move over to EBS instead of continuing on with NVMe. So first of all is the cost per gigabyte of storage is lower as we do not fully utilize the performance of NVMe. So with the base throughput and IOPS configuration of EBS is way cheaper as compared to using instant storage, and that is exactly what we need. We don't need any additional performance. Also, using EBS will help to decouple the size of an instance in terms of CPU and memory from its storage capacity. So which is something we couldn't achieve with the previous design. So this all of these help to lead to cost savings by allowing us to independently right-size our instance type and their according storage. So this separation also enable us to have new use cases that require disproportionate amount of storage. We also have higher data availability in the sense that after a worker node rotation, a new Kafka broker will sync and catch up data faster as now it only needs to catch up based on data produced during downtime as compared to NVMe, because whenever we rotate a new instance, we have to delete the PPC, meaning that we have to wipe off the entire data of that broker and you have to catch up from the beginning again. So this will result in shorter maintenance operation for us. Also, we will have higher iteration speed and as well as lower inter-easy traffic costs because now there are less data to replicate from other brokers. Thirdly, it also eliminate the manual intervention with PV in TVC in Kubernetes as EBS-backed counterpart is automatically attached into new pods. Lastly, now we also have the capability to do data backup because it's now supported by taking snapshots of EBS volume. So let's go through how our cluster setup works now with EBS-backed data persistence. So with this, we also introduced a new component, which is called EBS CSI controller, something that will help to manage EBS-backed volume in a Kubernetes environment. So we are starting off by the Streamy Kafka operator that is going to create a new PVC. So this time it will specify the volume size as well as EBS GP3 as a storage class. So at this point of time, EBS CSI within the storage class, EBS CSI driver is also configured as the volume provisioner as compared to the local volume provisioner that we used previously. And also, the volume at this point of time is not provisioned until a pod claims the PPC due to the wait for first consumer setting. Then following that, the Streamy will also continue on to create a Kafka pod, and within the pod, it also references the newly created PVC. The pod will continue to claim the PVC when it is scheduled to start. This claim will then trigger EBS side controller, which will dynamically create a new EBS volume within the AWS PVC in the same AZ as the worker node where the pod is scheduled. The EBS volume is then attached to the corresponding EC2 instance. Following that, a Kubernetes persistent volume is created and reserved for the Kafka broker 1 pod. Lastly, the PVC is updated with reference of the newly created PV. At this point of time, its state is also changed to bound, and that together will allow the Kafka pod to start. So working with EBS, we also have a number of challenges. So first of all is EBS volume are AZ specific. So for example, if we are having a worker node in AZ1, we cannot provision EBS volume in AZ2. That will not work, and we will not be able to mount the volume to the instance. So to solve that, we already maintain one ASG per availability zone. So that is not exactly much of an issue, but that adds up to the complexity of our setup. Secondly, whenever we try to scale our EBS volume, be it increasing the volume sizing, increasing the throughput, or provision additional IOPS, AWS will impose a scaling cooldown within the volume itself. So this can range from 6 to more than 24 hours. So within that period, we will not be able to make any other further changes to the volume. So to overcome this, whenever we do scaling of our volumes, we would usually scale them generously with a security margin. But by doing so, it also brings us to the last challenge with EBS that we need to consider. Because if we over-provision the volumes, it will also lead to cost inefficiency. And with the nature of Kubernetes persistent volume, scaling down the volume is currently not supported. So if we over-provision, we have to stick to it until we have the need to scale again. So with that, for temporary storage need, not a long-term one, we would usually scale the cluster horizontally by adding additional broker. So that with that, we avoid scaling the volume itself and solve our temporary problem. So with all of these solutions that we have implemented, there are a few operational improvements that we have benefited from. So first of all, the process is now, the entire process is now simpler and less error prone because we have completely eliminated the human aspect of the process. And together with that, now we only need to rotate each instance in sequence with no need for manually reconfiguring the target group or the node network load balancer or deleting the zombie PVCs anymore. The whole process is also now faster because the time between each instance rotation is limited to the short amount of time it takes for the restarted Kafka broker to catch up with the new data, as compared to before you have to catch up the entire data, which we have had to deal with, and it can get as bad as taking 12 hours for it to catch up. So if we were to perform this at night, it will take until the next day noon. And lastly, we are also benefited from a little bit from cost efficiency because now there is less data to transfer across AZ, which is something charged by AWS. So going back to the original challenges of our initial setup. Now, whenever a worker node is rotated, naturally a new node will be spun up and the new Kafka broker will be scheduled onto the new node. But this time, there are no longer connectivity issue because configuration of NLB is already set up, and we already have graceful shutdown, so there are no abrupt disconnection to our client. Also, now the new broker port is also automatically attached to the previous persistent volume, so we don't have any issue with storage anymore. So with all that improvement, there are still a lot of enhancement we can make, and there's a lot of room to keep moving forward. So first of all, we have not fully utilized node termination handler yet. We can there are a few aspects such as webhook that we can utilize. So as soon as node termination receive any event, you also can trigger webhooks, which is then we can develop application to proactively spin up EC2 instances. So we don't need to wait for cluster autoscaler to scale out the ASG anymore. And potentially we can reduce the 4 minutes delay that we are currently facing. Second of all, with the webhook, we can also start sending out notification via communication channel. So for Grab, it will be Slack, so that our engineers will have higher visibility of such events. So moving on with that, we also plan to utilize Carpenter. So Carpenter help us solve a few challenges. So comparing Carpenter and cluster autoscaler, Carpenter has proven to us in other use cases to provision node faster, because they will spin up EC2 instances directly via EC2 API instead of scaling out ASG and wait for the entire flow to work. With that, we also eliminate the need for ASG, so that then Carpenter is also able to handle the EBS AZ bound logic. So it also helps us to reduce the complexity of ASG with EBS. Also, Carpenter also had the capability to handle termination event exactly like how node termination handler is doing them. So we can also eliminate node termination handler as well. So we are dropping 2 components for 1. The third improvement that we can make is that we can have some form of EBS auto scaling. So now whenever we are doing scaling, like adding additional volume sizing or increasing throughput, our engineers are monitoring the metrics and doing so manually. So we are hoping that we can have a form of better monitoring and auto scale the volume automatically. And lastly, because we are now still facing with the 10-second delay of NLB health check problem, there is a configuration of Kubernetes which is called publish not ready address that potentially will reduce the 10-second delay by usually when the pod is in ready state, then the new private IP address of the pod is propagated onto the endpoint resource. But with this configuration, Kubernetes will do so as soon as the pod is scheduled, and it will not wait for readiness, pod readiness, which will potentially reduce the 10-second delay that I've been talking about. And that also concludes my presentation for today. Thank you, everybody.
Thank you, Thang. I really appreciate that. If you have any questions for Thang, wherever you're viewing this, feel free to put your question in the chat and we can answer it live. We do have a few minutes before we jump into the quiz. If you do have a question, again, just put it in the chat and we can do that. There is one here that from the beginning, which is for you, Thang, which is sorry, I'm just making sure we're still streaming.
No worries.
It seems like Diogenes says we might be disconnected, but I'm going to go ahead and just ask you the question anyway, because I think we're recording it anyway. The first one was, did you try any other deployment methods or operators before deciding on Streamy?
So our initial setup was actually on a very basic deployment method with barebone EC2 instances on AWS. So then we decided to move on to Kubernetes, and initially we have tried to deploy with the usual stateful set method, and it worked for a while, but with Streamy, everything has been a brief, and a lot of things has been automated, and we love it.
Got it. But no other operators then. Streamy was the first one.
Yeah, we have gone with Streamy since the beginning of our Kubernetes journey. So yeah.
Got it. Okay, there's another one here around the limitations of EBS. You mentioned the 3 limitations of EBS and that you're using Carpenter to alleviate the ASG one. With regards to the other 2, have you looked at any other storage solutions either in the DOK space that could help you alleviate these, or are you sticking with AWS specific solutions?
So because we are when we are looking for other solutions to replace the instant store, EBS came up on top because first of all, it's a solution for AWS, which is something that we have been a cloud provider that we have been heavily utilizing. So then it also has the capability to mount the volumes automatically for us whenever we do instant rotation. So that's one of the key points that we consider EBS. With the other 2 challenges, is a challenge when we are using it, but it's something that we can overcome. So it's not too bad for us, and that's why we decided to go ahead with it. Yeah.
Got it. And a follow-up to that one, which is, could you explain more how Carpenter helps reduce the EBS complexity with ASGs?
So because previously with the cluster autoscaler setup, you will need to manage 1 ASG per availability zone. And with that, whenever we scale the instances, we will need to make sure that we are scaling the correct ASG, else the volume won't mount back. And because of that, there is a complexity there. So with Carpenter, because they are not following the ASG kind of deployment of EC2 instances, then it also have the capability to detect if there's the existing EBS volume being mounted to the instance itself, then it will know how to spin up instances in the exact same AZ. So we are shifting the problem over to Carpenter to handle it. And yeah.
Got it. Yeah. Great. Well, I think that's the questions that I saw for now. I believe. Oh wait, we have one here. One more here before I move on. How are you approaching the resize of EBS volumes? Are you resizing only a particular broker's volume or all broker volumes?
Okay. So when we are doing resize, we would follow the previous practice of using instant volume, is that in a sense that when we resize one, we have to resize for all. So that will also reduce the complexity in a sense that we don't have mismatch configuration among our brokers, as well as they are leaving no room for any incident to happen in case some traffic spike, and then the other brokers are not having enough storage to work.
Got it. Okay. Hopefully that answers your question, Frantisek. And I think that brings us to the end of the questions, at least for now. And we can jump into the quiz unless I see any more pop up here really quick. All right. All right, let's jump into the quiz. I will ask Diogenes to pull up the quiz entry. And you can scan this QR code with your phone and enter the code to get into the quiz. Now, I mentioned before that the fastest to answer the questions will win the t-shirt. We won't start the quiz until we get a few people in the actual quiz platform. So while you're doing that, you can go ahead and scan and wait for the quiz questions. And then once we get enough people, I'll read off some of the quiz questions as well. Again, just a few basic questions and we will jump in. We got 3 players. Let's try to get a few more, hopefully. 4, I like to see it. Yes. All right, first question. DoK Day will be co-located at KubeCon in Utah. It is taking place on what day? October 12th, November 12th, or December 12th? Who remembers what we mentioned before? Or maybe you already know this anyway. Nice. Most people. I love it. All right. Elsa's in the lead. All right, second question out of the 3. What is the deadline for submitting proposals to the DoK Day? So this was the CFP for DoK Day co-located with KubeCon. CFP, June 14th, July 14th, or August 14th? Hopefully it's not June. Great, everyone got it right. That voted at least. We have a close race. Elsa's still in the lead. All right, last question. What talk topics are we looking for in DoK Day CFP submissions? DoK application development, emerging and advanced in DoK and DBAS. Day 2, operations, I guess. Use cases and best practices. All of the above. Sort of a trick question, I think. All right. Look at that. Johanna is the winner. Congratulations. So this is somewhat anonymized. So if this is your user, please make sure and reach out to the DoK community or email if we have one here. I forget if we have one to share. But reach out to the DoK community to let us know that was you. And we'll make sure to get you your t-shirt. All right, that is the end of today's presentation. Again, thank you, Thang. Thanks for everyone who is joining for the stream, and have a great day.
Thank you, everybody.